Hi students, today I am discussing about SNAE reaction. SNAE reaction. Nucleophilic substitution. In that first addition, next elimination. This SN nothing but substitution nucleophile. If you can reverse also we can study nucleophilic substitution. In this nucleophilic substitution, first we have to add, next elimination. That is called AE, addition elimination reaction. Well known reaction is, this is chlorobenzene. This chlorobenzene react with the NaOH at nearly 623 Kelvin and high pressure nearly 300 atmosphere pressure. And next first step, this is between NaOH and 623 300 atmosphere. Next step is H plus you can add or water you can add. It means you can add the H plus or water. Then we will get here, in this OH, here substitute, here Cl and Na, that will convert into NaCl. To neutralize that reaction, we have to add water or acid. In this reaction, actually this leaving group is not easily eliminated from the benzene ring because of the resonance structure. Due to this resonance structure, it forms partial double bond character. If you want, I will show here. Double bond, double bond, double bond. Here chlorine, lone pair of electron. This lone pair of electron comes to here, this will be comes to here. Then we will get here negative charge, double bond, double bond, double bond, Cl, lone pair, positive charge. So due to this resonance, again this will be delocalization of pi electron takes place. This bond breaking is difficult, and it also having the sp, before that here sp2 carbon. This is now also it is sp2 carbon. Carbon having double bond mean it is having sp2 carbon. Bond length is decreased. When bond length decrease, that is easy to break is not possible. Therefore, this chlorine or fluorine, bromine, iodine directly present on the benzene ring, it is difficult to leave. That's why we are using the drastic condition, that is 623 Kelvin, 300 atmosphere pressure. And this should be highly basic required, nearly equal to 14 pH. pH should be equal to 14 in strong basic in nature, then only this reaction is possible. Otherwise, no. So if you observe now, to make into this reaction easy, if you use high temperature, high pressure condition, it is difficult to handle. That's why we have to reduce this condition. When we will reduce this condition, if any electron withdrawing look like NO2 present at ortho para position, then automatically its reactivity increases. Why increases we will discuss later. Now, if electron withdrawing group present at ortho para position of this group, haloarene, that may be chloro or fluoro or bromo, then its reactivity increases. Now, I am taking now this Cl only, NaOH, now 443 Kelvin, and second step is H plus red or anyone, no problem. Then, but here you can write the NO2 at para position, or you can take anyone. Now I am writing or here. You can take ortho also. Both reactivity will be same. NO2 group at ortho position or para, both reactivity nearly same because they are equivalent resonance structures. Now we will get here, this is OH, here NO2 group. Otherwise, if ortho position is taken, that time we will get here OH and NO2. Here also pH we have to maintain high pH only, that is nearly 14 pH. Highly basic condition is required. Strong basic character, even that is act as somewhat a good nucleophile type here. Now because if you observe this rate mechanism, it is second order kinetics. In second order kinetics, strong nucleophile required and high concentration required. That's why high pH maintenance is compulsory, it is required. Next, one other extra NO2 group I want to increase here. NO2, NO2. Same NaOH, and here 368 Kelvin temperature in the second step, H plus. Then this is also nucleophilic substitution reaction on benzene. Here OH, NO2, and here NO2. Now due to this electron withdrawing group, here reactivity increases because this leaving group in resonance structure, if you observe, somewhat stabilize that carbon ion. That's why electron withdrawing group required, and here temperature is step by step what happened here, decreasing. In this condition, pH we have to maintain nearly 10 because its reactivity somewhat increase. So if you maintain the less basic nature also, it is easy to react to form the product. Now one more electron withdrawing group if you increase OH, sorry, now we have to write the Cl reactant, NO2, NO2, NO2. This is react with the NaOH and just warm it. If you warm it at the using normal H2O or H plus, then we will get here picric acid. OH, NO2, here also NO2, here also NO2. It means when electron withdrawing groups are at orthopara position, reactivity increases, nucleophilic substitution reaction is easy. Now the question you may ask, if NO2 group present at meta position, then what will happen? That is a question. Then its reactivity increase or decrease. We will discuss with the one example. And one more thing is here, I took here chlorobenzene. If fluorobenzene taken or bromobenzene taken, reactivity increase or decrease. That is also question. Now we know that in SN1, SN2 reaction, generally larger group is a good leaving group or weak base is good leaving group. If you take the HF, HCl, HBr, then or HI, then H, which is a stronger acid, HI is a stronger acid. Then if you write its conjugate base, I minus is a conjugate base. Stronger acid gives weak conjugate base. So weak conjugate base means that is a good leaving group. Then we are expecting that I minus is a good leaving group. Then we have to take in this reactions, whatever the phenol preparation or trinitro 2,4,6 trinitrophenol, that is picric acid preparation, we have to take I only. It means on benzene the leaving group should be I. It means that is more reactive if you consider. But in this reaction, that is not correct way, because if you take the reactivity order, now I am taking one minute. In this reactivity order, I will write some word down. In this reactivity order, one is fluorobenzene, another is chlorobenzene, and next one is bromobenzene, next one is iodobenzene. Themselves they are very less reactive in nucleophilic substitution reaction. That's why at least one electron withdrawing group. Now the question for the students, how many electron withdrawing groups required for this nucleophilic substitution reaction on benzene? At least one electron withdrawing group required. More than one also, that is better reactivity for nucleophilic substitution reaction. That's why I am writing here NO2 group at all the fluoro, chloro, bromo, iodobenzene. Now this is a reactants. Now which should be the good leaving group? If this question may be given, which is a correct order of reactivity means many of the students may answer this is a more reactive, this is a less reactive because this bond is shorter, breaking difficult, this bond is longer, breaking what easy. But this is not the correct answer. Actual reactivity order is this one. Then you may be confused now. What is the question arises for you? Already we studied that I minus is a good leaving group, but now we are telling this is a good leaving group, how it is. So whatever this order you may be studied for the carbocation formation respective. But in this nucleophilic substitution reaction on the benzene, that is aromatic substitution reaction on this, that time it formed carbon ion, not carbocation. That's why its reactivity is totally different. Now, consider I will take the one is fluorobenzene, another is chlorobenzene, and I will compare the reactivity. This is considered fluorobenzene. At this position, we have this NO2 group in the form of Lewis dot 6 I wrote here. Now consider one of the nucleophile, that may be OH minus or anyone consider. I will write Nu only. This is nucleophile. If you want OH write, you can write methoxide ion also write, no problem. Anyone you can write or OH minus write, that is your choice. Like this, anyone nucleophile you can take. For example, if I take methoxide ion, okay, no problem. Because now we are doing the which one? Nucleophilic substitution means one group will be substituted by another group. F will be substituted with the methoxide ion. Then what is happening here? This reaction is slow step here. Slow step means what we call that is RDS, rate determining step. Then we will get here, immediately this pi bond will be shifted here. Then we will get here negative charge on the ortho position. Double bond, here we have one fluorine and we have that is methoxide ion. Yes or no? And at this position we have N double bond O. You can write coordination covalent bond also like this one, no problem. Okay. So now this is resonance stabilizer like this. Negative charge here. This bond will be comes to here and this will be comes to here. Then we will get another resonance structure. Double bond, N positive charge, O minus and O minus. Here double bond, not double bond, sorry. Here F and here should be OCH3. Now carefully observe. I told that F is good leaving group than the chlorine in this reaction, nucleophilic substitution reaction. Reason why fluorine is required in this case means this is a carbon ion form. This carbon ion is stabilized by electron withdrawing group. That's why one electron withdrawing group increases, its reactivity also increases. On NO2 group, this is minus I effect, that's why it is stabilized. So this stabilizer form. Next, it is leave. How it leave? When it comes to here, this will be comes to here, this will be comes to here, this will be out. Then we will get, this is a double bond, OCH3 and N, and this is double bond O minus Na plus. And if you observe here, negative charge on the oxygen atom, according to the resonance structure, if negative charge present on oxygen, that is more stabilized form. If you take the same chlorine, now I am writing with the chlorine. Now if you take the chlorine, then here chlorine, if you take here chlorine, then here chlorine, like this, and minus here, before the F minus is here. Now if you take the Cl, then Cl minus, this is a leaving group. Now the question is, F is more electronegative than the Cl, that's why this carbon ion is less stabilized with the chlorine. Therefore, this is a more reactive towards the nucleophilic substitution reaction in benzene ring. But chlorine, fluorine, bromine, iodine reactivity what happens? Decreases. If iodine present here, this carbon ion is very destabilized form. That's why this is a reactivity order. Now you may ask the question. I told that if this group present in NO2 group in ortho and para position, like this reactivity. You can write with the ortho position also, same reactivity. But it may be present on meta position. Then what will happen? That is also we will discuss now. Consider I am taking now fluorine only, because fluorine is good living in this reaction. Double bond, double bond, double bond, here N double bond or O minus Na plus double bond O. Now this is F, fluorine. Now consider same methoxide ion only we have taken, consider no problem. Then it will becomes to here, this will becomes to here. Then we will get here a carbon ion. This is a negative charge. Here the fluorine, here the OCH3, here double bond, correct? And next N O minus and double bond O, here positive charge. Now consider this carbon ion is not conjugation with this NO2. Reason here this lone pair of electron, next single bond. That's why this pair of electron will come in this direction. Like I am not writing like this steps. So here only I want to explain you to understand how it is leave. But this single bond, so this NO2 is not conjugation with this negative charge or carbon ion. That's why there is no effect, there is no stabilization through meta. That's why this is not affect the reactivity of this halobenzenes. Therefore, it is less reactive compared with, now I am writing here like this 3 order. Here F NO2, next F NO2, next here F, here NO2. What is the reactivity order of these three? These two are equally react, and these are more reactive than this meta position NO2, because already we understand with the its resonance structures. Now, okay, before that we discuss this is a reactivity. This is a chlorobenzene. This is a chlorobenzene with NO2. Next, chlorobenzene with the NO2 and NO2. Next, chlorobenzene with the NO2, NO2, NO2. If you compare, all are having the same chlorine atom, but 111 NO2 group increases, reactivity increases. Now the one more question. If NO2 present at this ortho position, already told you that ortho or para position both reactivity same. Then if you want to write, these are equal with ortho position NO2 also. Okay, this is a reactivity mechanism. And this elimination reaction, whatever the first nucleophile attack, that is a slow step. Next, whatever the Cl minus left or leave, that is a fast step. Now, they may ask the kinetics, meaning what is the order of reaction. In this slow step, two molecules are participating. It means this haloarene. Can I write like this also? Okay, because now with this mechanism not required, so I will remove this. Now consider kinetics of this reaction. We can say here R is equal to K haloarene and here nucleophile. Therefore, order of reaction is 2. 1 plus 1, that is 2. This is a very important part for understanding nucleophilic substitution reaction on haloarenes, that may be fluoro, chloro, bromo or iodine. Okay, so I hope you understand well, and keep in mind fluorobenzene is highly reactive. When any electron withdrawing to like NO2 or any one electron withdrawing to, because of in this reaction carbon ion form that is stabilized with the electron withdrawing to. Thank you very much.